On July 2nd, 2026, a heat wave pushed the Mid-Atlantic grid to an all-time record, past 168,000 megawatts, beating the old mark from 2006. To hold off blackouts, a federal emergency order stood ready to tell the region's biggest power users, data centers included, to switch onto their own backup generators. The most advanced computers ever built, told to stand down first. Welcome to our new channel. My wife and I make these episodes to show you the systems hiding in plain sight, and this is our very first one. I'm Alex, and this is Unseen Systems. So why does one AI cluster draw as much power as a small town, and where does it all go? Start with the smallest honest unit, one rack of chips. As of 2026, a single NVIDIA GB200 rack pulls about 130 kilowatts. These numbers keep climbing with every hardware generation, but the physics underneath does not. And 130 kilowatts is already the continuous draw of about 100 homes in one cabinet you could stand beside. Line that rack up against the houses on your street. One cabinet, humming in a cold aisle, eats the same steady power as roughly 100 of those homes put together: lights, fridges, ovens, air conditioning, all of it. That is the atom this whole story is built from. Now stop thinking about one rack. To train a frontier model, you wire tens of thousands of chips into a single cluster. Meta trained Llama 3 on 2 clusters of 24,576 H100 GPUs each. A haul like that draws on the order of 30 megawatts, a rough estimate, but the right ballpark, roughly a small power station's output feeding one room. Stack enough of those hauls into one campus, and the load reaches a full gigawatt, 1,000 megawatts running non-stop. On a continuous basis, that is as much electricity as a mid-sized city of about 750,000 homes, all pulled through a single fence line. That is the small town from the question, and it is not a metaphor. It does not build up slowly. It arrives all at once. So follow that power in. It does not come from a wall socket. A gigawatt campus needs its own dedicated substation right at the fence line, where a high-voltage transmission line arrives at something like 230,000 volts. Why so high? To cut the losses on the way in, and we will see exactly why once we reach the load. At the fence, that first substation steps 230,000 volts down toward around 13,800, what the industry calls medium voltage. And this single object, the substation, is the most contested, slowest to build thing on the entire site. Everything downstream lives or dies on getting it energized. Inside the medium voltage switchgear, that 13,800 volt supply is split onto a bus and fanned out across the campus, one incoming river of power, divided into the feeders that reach each building. Still far too high to touch, but low enough now to route around a site. Then at each building, a unit transformer drops that medium voltage again, down to 480 volts, the level the electrical gear inside can actually accept. The exact numbers shift from site to site, but the logic never does. Every transformer is a physical box, and each one gets smaller and more numerous as we close in on the chips. Next, the power passes through a wall of UPS units, uninterruptible power supplies, and their batteries. Their job is not to run the site for hours, it is to clean the power up and cover a blink. If the grid so much as flickers, the batteries carry the whole load from milliseconds to a few seconds until backup generators can start. Hold onto that row of generators. It comes back later, and it is the whole point. From there, a power distribution unit, a PDU, makes the final step down to 208 volts and hands it to a busway, an overhead bus bar running above the aisle that carries it the last few meters straight over the tops of the racks. And at the end of that busway sits the rack itself, about 130 kilowatts in a single cabinet, running so hot the whole thing has to be liquid-cooled. That is the end of the line transmission tower to GPU, one continuous copper path, stepped down 3 times along the way. So why step the voltage up and down all the way along that path? To fight one equation: line loss equals current squared times resistance. Push the voltage high and the current falls, and the wasted heat falls with the square of it. So you move power at high voltage and low current over distance, and only drop it to low voltage, high current, right at the load. That whole chain of transformers exists to obey that single rule. Now here is where the whole story turns. Almost everyone assumes the thing holding AI back is chips. Can you get enough GPUs? But an operator can buy 100,000 GPUs and stand the building up in a matter of months. That part is fast. The wall is somewhere else entirely. Every big new load has to wait in what is called the interconnection queue, a multi-year study and approval backlog the grid operator runs before you can plug in. And that wait has blown out. For projects built in the early 2000s, it ran under 2 years. For projects built in 2023, the median had climbed to about 5 years. Months for the chips, years for the connection.
The typical wait has risen to a median of 5 years for projects built in 2023.
So the bottleneck was never really the silicon, it is the connection to the grid. An operator can own the chips, own the building, and still sit and wait years for the utility to switch it on. The wall is the queue, not the chip. And the queue is jammed almost past belief. At the end of 2023, more generation and storage was waiting in line, about 1,570 gigawatts of generation, plus another 1,030 of storage, than the entire United States grid has installed today. Historically, only about a fifth of the projects that join the line are ever actually built. So an operator with money, chips, and a 5-year wait does the obvious thing. They stop waiting on the grid and build their own power. Which brings us back to that row of generators. Behind every big AI campus sits the string we just traced: UPS units and batteries, and behind that, out on the pad, rows of diesel generators. On paper, pure insurance. For the rare day the grid fails and the site has to carry itself for hours. But look at how many there are now and what they have quietly started doing. The scale alone is startling. Backup generator capacity at US data centers nearly tripled, from about 20 gigawatts in 2018 to roughly 55 by 2024. In Virginia alone, the densest data center cluster on Earth, there are now more than 10,500 permitted generator units, about 27 gigawatts of diesel, sitting behind the server halls. And this genuinely surprised me. That backup is increasingly dispatched routinely as a balancing tool. When the grid is tight, operators fire the generators to shave what they pull from it, and to take part in demand response programs, running diesel not for a blackout, but on an ordinary strained afternoon. The insurance has quietly become part of the grid's own machinery. And that lands us right back where we opened, July 2nd, 2026. A mid-Atlantic heat wave drove PJM, the grid operator for the region, to that preliminary all-time record, roughly 168,000 megawatts of demand, edging past the old mark set in 2006. The whole system was running right at its ceiling. To keep from tipping over, a federal emergency order under the Power Act stood ready to direct large loads, anything drawing 50 megawatts or more, to switch onto their own backup generators within 15 minutes. Hospitals, 911 call centers, and water plants were exempt. The data centers were not. Public reporting says they were put on notice to stand ready, not that any were actually forced off, but the message could not be plainer. On the worst night, the AI stands down first. Line all of it up, and one fact reframes the whole thing. The interesting part of an AI cluster is not that it burns a lot of power. It is that it is barely a computing project at all. It is a power delivery project, with computers bolted on at the far end. The moment the chips are easy to buy, the entire contest moves to copper, transformers, and a queue. That leaves one plain way to keep the whole thing. The chips arrive in months, the grid connection takes years, so the real machine is the power hookup, and the diesel row behind it is the emergency brake the grid has quietly started to lean on. So an AI data center is not a brain that happens to need electricity, it is a small power plant's worth of load, wearing a computer as a hat. Open a satellite view of any big one and look for the thing the headlines skip. Out back, the long row of diesel generators we just watched get called up. Out front sits the substation that swallows a town's worth of power. That is where the real story lives. Thanks for watching.